So in section 3.4, make sure you have your notebook, pencil, periodic table, and calculator out. We're going to actually do some calculating during this one, even more during the next video. This one is called Avogadro's number and the mole. Write down the title, put it in your table of contents, and you can start writing down the notes right here. So even the smallest samples that we deal with in the laboratory contain enormous numbers of atoms, ions, or molecules. So for example, 5 milliliters of water, just about a teaspoon, contains more than 2 times 10 to the 23rd molecules of water. Way too many for you to ever count. And so chemists have come up with a counting method that helps take care of this number of things in the nanoscopic world. So then in the macroscopic world, we can just measure out 5 milliliters and know how many particles we actually have. So just like the number 2 means a couple, 12 means a dozen, 144, maybe you knew this, it means a gross. We have a number in chemistry. The number is 6.022 times 10 to the 23. And this number is called the mole. We use this number because it's really handy for counting atoms, molecules, or ions, because there are so many of them in just a small sample of whatever we're working with. So this can be used to count atoms, molecules, or ions, or whatever we have of lots and lots of things. And it turns out it's really handy too, because one mole, 6.02 times 10 to the 23rd things, is the same whether you count atoms of carbon, molecules of water, or NO3 minus, which is called nitrate ions. It's the same. It turns out it's super easy to find these on the periodic table as well, because there's a link. It turns out that the formula mass, also known as the molecular mass, the molar mass, the atomic mass, also known as the formula weight, the molar weight, the molecular weight, the atomic weight. Turns out that those masses are 6.022 times 10 to the 23rd things, or 1 mole of them. So let's take a look at chlorine on the periodic table. Chlorine has an atomic mass of 35.45, which means that in 35.45 AMUs of chlorine, there is 1 mole, or 6.02 times 10 to the 23rd chlorine atoms, or 35.45 grams in the macroscopic world. And so now we can measure out that mass of chlorine and know exactly how many particles there are, how many atoms or molecules or ions. In this case, it happens to be atoms of chlorine. Take a formula, for example, like carbon dioxide, CO2. Carbon dioxide has 44 AMUs. If you add it up on the periodic table, carbon is 12, oxygen is 16, so 16 times 2 plus 12 adds up to 44. So that's its formula mass or molar mass. That would be 1 mole of CO2 molecules, or 6.02 times 10 to the 23rd of them, or 44 grams. The periodic table is the link. The periodic table is the piece that allows you to take something from the macroscopic, measurable in grams, and bring it to the nanoscopic, number of particles that you can't even see. So on your notebook now, I'm going to ask you to leave lots of space. Go to a new page if you need to, because we're going to write a large diagram in the middle of the page. And then start in the middle. Just skip a bunch of lines right here and start in the middle of this diagram. Start right here with a box that says the mole in it. Draw a couple of arrows going up here to the left and write the words atoms, molecules, or ions. And then down here, draw a couple of arrows and put mass in grams right down here. And then you can put PT, standing for periodic table, over here to the right, because that's the link between the mass and the moles of some substance. And you can write the mole number, also known as Avogadro's number, 6.022 times 10 to the 23rd, right up here between the mole and atoms, ions, or molecules. And interconversion between these three things back and forth is actually relatively simple. So this number is called Avogadro's number because the scientist Amedeo Avogadro was the first one to come up with that that numerical value, and people didn't really believe him when he first came up with it. But after he passed away, then it turns out that everybody pretty well accepted it. So we'll see lots of detail of this outlined in your periodic table. And if you take your periodic table and you open it up, you can see that there's a more detailed piece right here of what you just wrote down. Here's the mole, and then here's the arrow going to mass in grams. And then here's the mole going to number of things, molecules, atoms, ions, particles. And you can see that that uses Avogadro's number, 6.02 times 10 to the 23rd. It even gives you the fractions right here, or the ratios right here, to go between the two. MM right here stands for molar mass or molecular mass. So make sure that you know, maybe write yourself a little note in there. That means add them up on the periodic table. We'll get to this side over here when we get to chapter 10. It allows us to convert to volumes of gases as well, as long as we're at certain conditions. But for right now, this is really handy to know where it's at. We'll do one example problem on this video, and then the next video we'll do lots and lots of examples from the textbook using the calculator as well. We'll use the calculator on this one, so please take your calculator out, and then you'll need your periodic table as well as we follow along. And I'll pause to give you a chance to try it on your calculator as we go. I'll use this kind of calculator because it's got a screen on it, but you don't have to have that kind. So first of all, 22 grams of CO2. Please calculate the moles of CO2, the molecules of CO2, and the atoms of oxygen that are in this particular sample. First, start way on the left-hand side over here where the red line comes down and write down your given amount, 22.0 CO2 grams. Put a multiply side, put a line. And then go ahead and take a look at your mole wheel or your mole calculator here and know we're going from grams to moles. So identify where you are on here. We're at grams or mass right here, and we're going to moles. And so we're going to use the MM right here, the molar mass, and we're going to use 1 mole, that type of fraction right there. A good way to do it is take the units that you have and put them in a position where it's going to cancel, grams CO2, and then put your desired units up here on the top, which is moles of CO2. And we know that the link is the periodic table between grams and moles. And so in 1 mole, we look on the periodic table and we add up carbon, which is 12, oxygen, which is 16, but you have to add up 2 of them because there's 2 oxygens. So 16 plus 16 plus 12 gives us 44. So the 44 goes with the grams. And if you want to write yourself a little note, because maybe you've never done these kind of problems before, you can say, always put the grams as the periodic table number. So if you're wondering what to put there, always be like, did I find it on the periodic table? If you have grams down there and you didn't find it on the periodic table, you probably did something wrong. So I made this one pretty easy, 22 divided by 44. You can go ahead and do that on your calculator if you want, but hopefully you get 0.5. So here we have 0.5 moles of CO2. Step number 1 done. Number 2, we want to know the molecules of CO2. And we can go ahead and start with 22 grams if we want, but maybe we'll recognize that to get to molecules of CO2, we need to know the moles. Notice there's no way to go directly from grams to molecules. You have to go through the mole. That's what makes the mole so useful. It's kind of the hub of everything else. And so I'm actually going to start with my answer right down here, right way on the left-hand side where the red line is, 0.5 moles CO2. Put a multiply sign, put a line. Put moles of CO2 in a position where it's going to cancel because that's the units that I have. Put my desired units here on the top. And the thing that I desire are molecules of CO2. So write the word out, molecule, CO2. Put the units in there. Take the time to write the units out. And everything will be okay. And then you'll notice that our conversion factor is the Avogadro's number. And we're going from mole to number of things. So that Avogadro number goes on the top and the 1 mole goes on the bottom. Because in 1 mole of anything, there are 6.02 times 10 to the 23rd molecules. Now, this is maybe one of the few times I'll do this, but notice how there's an E in here. That's because when I put that in the calculator, 0.5 times 6.02, I'll use the EE key right here. So second EE puts the little E on the screen right there, and then I can just put in 23. Don't put in times, 10, caret, don't do all of that. it'll mess up your whole order of operations. Just put in the enter exponent right here. It has a little blue EE on this particular calculator. Some other calculators have just an E. Some calculators have different symbols for the enter exponent. But please don't use the caret part. Don't use the times 10 part. Otherwise, you screw it all up. It ends up being 3.01 times 10 to the 23rd. So I can interpret that E right there, if you can see the small E right there, as the times 1, 0, and then 23 is my exponent. The E just indicates that's the exponent. And then number 3, the last one, this one's kind of tricky, atoms of oxygen. So you'll notice that for every carbon dioxide molecule, there are 2 atoms of oxygen. See this small 2 right here? That indicates that there's 2 of them. And since I already know the molecules of CO2, I can find out how many atoms of oxygen are in there simply by using the formula. So this doesn't use the mole wheel at all. Just start with the 3.01 times 10 to the 23rd molecules. Remember, a molecule is a collection of atoms, and we have a collection of atoms right here. And I want to go from molecules, so put those in a position where it's going to cancel, to atoms. So put your units in first, and then you can never go wrong. And it happens to be atoms of oxygen, and I have molecules of CO2. And in every one of these CO2 molecules, there are 2 of these atoms. So put a 2 right there for the O. Now I'm just taking 3.01 times 10 to the 23rd times 2. You can go ahead and type that in your calculator if you want. Otherwise, just know that you ignore the times 10 to the 23 part and do 2 times this number, and you end up with, oh, look at that, 6.02 times 10 to the 23rd atoms of oxygen inside that sample of 22 grams of CO2. Turns out to be 1 mole of oxygen atoms. Good luck with your mole calculations.